All right, so here we go. All right, this question says, write the dissolving equation, equilibrium equation for iron 2 hydroxide and write its KSP expression. So, first things first is I write FeOH taken twice solid, solid on the left, ions on the right, solid on the left, ions on the right, solid on the left, ions on the right. Yes, don't change that. Don't ever change that. Even when you start with ions and you don't start with any solid, you still put the solid on the left and the ions on the right. Okay? All right, so we have this equation, and the KSP expression only includes aqueous things. Well, that would be these two guys and not the solids. I'm going to underline them with a little highlighter. Those two things are what get included, not the solid over on the left. So I write Fe plus 2 times OH minus squared. Do not forget your coefficients. This is a really good chapter for you to start thinking about, do I know my polyatomic ions and how to write ionic compound formulas? I think we experienced that yesterday, did we not, as we were working on the OWL? We discovered there's a lot of names, and I have to know my chemistry. I have to know how to write formulas. And so this is really the time where push comes to shove. We've had since June to learn polyions, to learn solubility rules. It's time. It's time. You cannot be a good chemistry student if you don't know your stuff. And you got to know your rules. You got to know your ions. Next chapter, we'll have to know all of our strong acids and bases all over again to be able to do that. All right. So just get off my soapbox. All right, here we go. How do we figure out the solubility when we have pure water? Pure water means this, 0 and 0 in the beginning. So here's the question. How much iron 2 hydroxide will dissolve? Not much. Not much. Okay. How much am I trying to get to dissolve? A big old fat, let's just use my yogurt spoon to see here. A big old fat spoonful of zinc hydroxide dropped into a glass of water, and I start stirring, and it's like powder in water. It's not going anywhere. It's not dissolving because it's insoluble. That's why it has a KSP. So we put some amount that we're trying to get to dissolve. It doesn't matter what amount you're trying to get to dissolve. It's not going to dissolve because it's insoluble. So write down anything right there. Write down kitty cat. Write down doggy. Write down the mole. How about the animal, not the mole? Okay, write down something, some amount. The Sing gauge calls it some. Isn't that what it says? It says some. And then pure water means 0, 0. So X moles per liter of the solid is going to fall through the cracks, creating X moles per liter of iron and 2X moles per liter of hydroxide. And so at equilibrium, you're going to have some amount of that. You don't even worry about it. X moles per liter of iron and 2X moles per liter of hydroxide. And how do I solve for X in any of my ice charts? Matt, you with me? How do I solve for X in any of my ice charts? I got to have a value, a K value. Got to have a K value. Well, we do. I gave you the K value up here as 5 times 10 to the minus 17. So what you do is you say KSP, which is 5 times 10 to the minus 17, will be equal to the amount of iron raised to the first power times the amount of hydroxide raised to the second power. And that simplifies into X times 4X squared, which simplifies into 4X cubed. And when I solve for the value of X mathematically by dividing by 4 and taking the third root of that value so that my 4 goes away and my 3 goes away, X comes out to be 2.321 times 10 to the minus 6 moles per liter. Austin, how would I change that into grams per liter? Multiply it by the molar mass of iron 2 hydroxide. So when I find X, I have found moles per liter the iron 2 hydroxide that does dissolve. Moles per liter. Questions on the Snagit out? Maybe want it in grams per liter. Or maybe they want to know how many grams if you have like 250 milliliters. Well, then that's just a ratio setup. Once I have moles per liter and I turn it into grams per liter by multiplying by molar mass, then I have a permanent ratio. And I can figure out what a different gram value would be for only 250 milliliters, which is a fourth of a liter less. Okay, got to know those little nuances there. All right, that's how I answer the first one. How do I answer the next one? Which is the same question, except it's no longer pure water. I've got iron 2 nitrates. So let's do a quick review. Let's do a quick review from Unit 2 of AP Chemistry, which says iron 2 nitrate is 100% soluble. So when we put it in water, there's a single arrow, which says it breaks up 100% into iron and nitrate. And if I start with 0.04 molar iron 2 nitrate in pure water, and that's always the understanding, minus 0.04 plus 0.04 plus 0.08 molarity. Why 0.08? Because it's a 1-to-2 ratio in that mole bridge. 2 of these for every one of those. Now, why am I not putting X here? Because it dissolves completely. I don't have an equilibrium sign up here. I have a single arrow sign. So that means the difference between equilibrium and a single arrow is that I can know the limiting reactant on this side is going to turn into 0. And what I have on this side, which the only important part is going to be the iron, the common ion part, I have those 2 values. I could care less about the nitrate. He's going to spectate anyway. This is the only part that matters for when I want to figure out the molar solubility of my iron 2 hydroxide with a common ion floating around. So this right here is all just review from Unit 2. I got to know that all the time. You do not have to write that down, but you have to know that all the time. So let's go now to this question, and let's use this 0.04 value right here of the iron. Let's just ignore that nitrate that is truly a spectator. You have to get very used to spectators in this unit. Fe, OH taken twice, solid, is trying to dissolve where there's already some Fe floating around. So that means he's not 0, but he is, because I don't have any hydroxide floating around. I still am going to take my spoonful of iron 2 hydroxide, Z amount, some amount, to try to get it to dissolve. It still does, bless you, the same thing. It does that, okay? And I thus get 2x, and then I get 0.04 plus x, but we're going to squiggly that out to save ourselves some math. All right, so I've got 2x and 0.04. I still do the same thing. I still plug into the KSP expression. I still say 5 times 10 to the minus 17 is going to be equal to 0.04 molar times 2x, and I still have to square 2x. Okay, the math becomes 0.04 times 4x squared. When you get finished doing all the math, x comes out to be 1.77 times 10 to the minus 8 moles per liter. Austin, how would I make that grams? Times it by the molar mass, and it would turn my molar solubility into a gram per liter solubility. Yes? No. Because you're sticking 2x inside and you're squaring it. Okay. Now, last one on this side. Same thing, but I'm not going to go show you that unit review because you don't need me to do that unit review. Sodium hydroxide is that formula. So 0.02 molar sodium hydroxide gives me 0.02 molar sodium ion, spectator. 0.02 molar hydroxide ion, not a spectator, a common ion. A common ion. Look up here. Everybody look up here. Look, 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 look. Spectator, common ion. Spectator, I get to ignore him. Common ion. Messing up the solubility, not pure water. All right, so FeOH taken twice. Solid is trying to dissolve, but there's a common ion present. 0.02 molar. No iron this time, but hydroxide this time. I still write down Z. I'm still trying to get some of it to dissolve. I still have this. Yes. Okay. We won't worry about the solid. We know what happens there. It is approximately Z. This is X, and this is 0.02 plus 2X, so I get to squiggly that. But please show that part, because AP exam people get very frustrated and angry when we don't tell you. You need to show them. You know it's plus 2X, but you're choosing to ignore that plus 2X. Okay. So KSP, which is 5 times 10 to the minus 17, is going to be equal here to X times 0.02 squared. Yes.
The I part of the equation on the product side, is that zero mean that not
There is. That just means initially, in the beginning, initially, before anything happened, initially, there was no iron present. And when you have pure water, there's no ions, period, present. There's pure water. When you have a common ion, it means that only one of your two ions already has an amount present.
This is what they have to be extra, like it.
The X and the C part?
Yeah.
Because here's what I have initially. Here's what's going to happen because there is an arrow which says there is going to be a reaction to reach what we call an equilibrium. When you're trying to get some of it to dissolve, a little bit of it's going to fall through the cracks, even though it's supposed to be inside. Right? Probably a little bit. Probably a little bit. Okay, X comes out to be 1.25 times 10 to the minus 13. And you know what? I did that without a calculator. I did that without a calculator. Okay, practice, practice, practice on that. All right, so here's the question. Let's go back to our 3 X's. We had the first X was 2 times 10 to the minus 6 moles per liter. The second X was 1.8 times 10 to the minus 8. The third X is 1 times 10 to the minus 13. What is happening to the solubility? It's getting less and less and less. So here's what happens. When there's a common ion present, it limits the solubility even more than it being insoluble. Okay, so here's your analogy. Are you ready? All right, the gym, pep rally day. All 2,000 of us want to fit in that gym. 2,000 plus of us, right? The gym is completely empty, pure water. Nothing in there hindering us from fitting in that gym. Okay? A second pep rally. There's a common ion in that gym. It's called, they let half of Brandon School, middle school, right, fit into that gym. We all 2,000 plus go try to fit in that gym. Fire marshal says, nope. There's already some common ion people. Can't do it. We can't all fit. That's what it means to have common ion. There's already some ions floating around, so it hinders how many can actually fall through the cracks, can enter into the gym. Okay? So when there's a common ion present, less of the substance can dissolve than when it's pure water. And you have to know that. That's just one of those little things with solubility that you have to know. Okay, let me go back real quick and make a statement if I can.